Hello and welcome. So on this video, what we want to do is extend what we had looked at in the previous video around drawing shear and bending moment diagrams for simple beams into what do we do when we have slightly more complex structures such as frames or like what we have in this example here where we have this small L section. So if this were a simple beam, and it just looked like this, well, we already have the tools. We know how to handle that. We know how to make those shear and bending moment diagrams. But what do we have? What do we do when we've got corners? Well, that's what we're going to look at in this video. In order to get started, we will start this problem the same way we start all statics problems, and that is by drawing the darn free body diagram. And so let's start in on that one. And so we'll draw our representation of the frame here, and we'll use red just to show our reactions so that they come up a little bit clearer on the video here. So I have a 10 kilonewton point load, a 5 kilonewton point load. We're going to call the left-hand reaction AY. We're going to call the right-hand one BY and BX. And let's put some dimensions on here just so that we can actually work through the statics. So this is acting 2 meters from AY and 3 meters from BY. And that point load is acting 2 meters above the pin reaction. So let's go ahead and solve for our reaction. So we have 3 reactions, so 3 unknowns, which is useful. This is a 2D statics problem, so we have 3 equations of equilibrium available to us. The first one we're going to use is just find the sum of the forces in the x direction. And if we look, we have a 5 kilonewton force minus bx. And all of that has to equal 0. So solving for bx, we get bx equals 5 kilonewtons going to the left. So that was pretty straightforward. Next one is, let's try to solve for AY, and we'll do it by summing moments about B. So we only have one unknown that we're dealing with this equation. So sum of the moments about B is equal to 0. And so if we're doing that, well, we have minus AY times 5 meters plus 10 kilonewtons. Let me put a Newton symbol up here for us. Plus 10 kilonewtons times 3 meters away. And then minus 5 kilonewtons times 2 meters, and that equals 0. Let's just do some quick expanding this out. So we have AY times 5 meters plus 30 kilonewton meters minus 10 kilonewton meters equals 0. This gives us 20 kilonewton meters. If we kick that to the other side and divide out by 5 meters, we find that AY equals 4 kilonewtons vertically. And let's go ahead and solve for BY. And we can find that by summing the forces in the y direction. So sum of the forces in the y direction, we have positive AY minus 10 kilonewtons plus BY, and all of that equals 0. We just found AY, so we can substitute it in. So we have 4 kilonewtons minus 10 kilonewtons plus BY, all of that equals 0. Solving for BY equals 6 kilonewtons, pointing up. Before we move on, it's always a good idea when we're doing these statics problems to do a statics check. And by statics check, just remember that is we're going to sum the moments about a point which we have not used before. And if we find that everything is in equilibrium, so essentially 0 equals 0, then we know we haven't made a mistake in our calculations anywhere, or anything like that. So it's always a really useful tool to do these statics checks for these statically determinate problems. So statics check. And the point that we're going to sum moments about, we'll sum moments about A because we haven't used that location yet. So plus sum the moments about A equal to 0, and just for reference, we could do it at any arbitrary point, but A seems to be a nice location for this. So summing moments about A, well, we have, and if we have counterclockwise as positive, well, we have A minus 10 kilonewtons times 2 meters plus By, which is 6 kilonewtons, and that is at a distance 5 meters away. Bx is 5 kilonewtons, but the distance to A is 0, so we'll just put that in for completeness. So plus 5 kilonewtons times 0 meters. And then finally we have this 5 kilonewton load, which is minus 5 kilonewtons times 2, and all of that equals 0. So this one crashes down to 0. We'll expand this out. We get minus 20 kilonewton meters plus 30 kilonewton meters minus 10 kilonewton meters equals 0. Minus 20 plus 30 minus 10 is 0, so we get 0 equal to 0. So our statics check works out. That's good. So we've done our first step in these problems, and that is we found our reactions, and now we can proceed with trying to draw the shear bending and axial load diagrams, and that's what this letter N stands for, is for the axial force. And just recall, this is the exact same procedure that we've used if we're just trying to find the shear and bending moment diagrams for a beam. We need to find the reactions first. So on this next page here, I've drawn what the shear and bend, what the free body diagram is of the entire structure, with the reactions put in, and I've got a little prompt here of, if this were a beam, we know what to do, but what would we do if now that we have this corner? Well, always when in doubt, draw the darn free body diagram. And so that's exactly what we're going to do. But, the question will come, Lucas, well, what free body diagram do we draw? And the simple answer is the one or multiple of them, which will help us understand the problem. And so free body diagrams that tend to help us understand the problems are simplify. And that's really what the whole purpose of drawing free body diagrams is to break down a complicated problem into manageable, more simple parts. And that's exactly what we're going to do. So I'm actually going to draw 2 different free body diagrams. I'm going to draw one around this vertical piece, and I'll make my cut just above the reaction here. And I'll call that free body diagram 1. And my second free body diagram will be the remainder of the structure. And if you recall back from analyzing trusses, this is very similar to method of sections, where we're going to break down the structure into multiple free body diagrams, expose the internal forces, and then use that along with our equations of equilibrium to try and solve the problem. So if I've got these two, let's draw the free body diagram at cut 1. So we'll go FBD 1, and we'll draw it with some thickness here just to kind of help illustrate a few points. And we'll leave a jagged edge there on the bottom. I'm going to say that this cut is right at the edge, so the distance is going to be 2 meters. Let's put on, so we know there's an external force of 5 kilonewtons here. And then when we make a cut, we expose the internal forces. As I said, just like if you're analyzing a truss with method of sections or method of joints, this free body cut through an element will expose whatever forces are internal, and then because everything has to be in static equilibrium, those internal forces need to be in equilibrium with any external forces acting on that element. So the internal forces in a beam, so if you remember for a truss, so if I may step back for a moment, for a truss, the internal forces are only axial. But for a beam, we can have bending. If we have bending, we can have shear, and we can have axial force. So drawing what those internal forces are, we would have a shear force, V. We'll have a bending moment, M, and we might have an axial force, N. So these are all the potential forces that we can have, and for those, we now need to solve and find out, do they all exist, and if they do exist, what their magnitude is. Before we go through and solve for these variables, I want to draw this second free body diagram. So if we have free body diagram 2, and we'll just, I think I can keep everything in frame here. So remember, free body diagram 2 is just the rest of the structure on the other side of this cut. And that's our cut here. And this distance is really small. We've made the cut right at the edge. We're going to call this distance 0, just for the analytical purposes that we have here. So putting on the reactions and the external forces which are acting on this piece of the structure, we get a 4 kilonewton vertical reaction, a 6 kilonewton vertical reaction, a 5 kilonewton horizontal reaction, and there is an applied load of 10 kilonewtons, which is 2 meters away from the left reaction. So that's all of the reactions and the external loads which are applied to this piece of the structure. But just like with free body diagram 1, if we make a cut, we're going to expose the internal forces. So one of the important things to know and to keep in mind is really Newton's third law, which is for every action there's an equal and opposite reaction. So if we have a moment going in the counterclockwise direction for the cut up here, well, that moment has to go in the opposite direction on the opposite side of the cut in order for everything to be in equilibrium here. Same thing, if the shear is going to the left on this side of the cut, the shear has to go to the right on this side. And if we have the normal force in compression here, so pointing up, well, it's got to go into compression down here, so that normal force has to be pointing down. And this is really the key concept for doing these shear and bending moment diagrams, or just understanding what the internal forces are in a structure when you go around a corner, is that everything has to be in equilibrium. So if you have an element on one side of the cut, the magnitude of that element will be the same, but the direction will be opposite. So really clear to see with the axial load here and with the shears, same with the moment. So we're going counterclockwise on the top, and we're going clockwise on the bottom. So, and the last thing to note is that if we have guessed wrong here, that's fine. We'll flip it, and that means that it flips on this side too. So now all we have to do is just apply our equations of equilibrium, and then we'll know what this magnitude of these moments or these shears are in the element. So starting with free body diagram 1, let's start with trying to solve what the forces are in the y direction. So if the sum of the forces in the y equals 0, well, the force that we have here is N. Well, that's going to equal 0, which means it's going to equal 0 on this side. And when we work out the equations of motion, the equations of equilibrium here, you will see that it falls out that way as well. Next we're going to look at is the sum of the forces in the x direction. And we have 5 kilonewtons minus V equals 0, so that we get our shear force equals 5 kilonewtons, which is good, is what we would expect. And then let's sum our moments at the cut. And we get a positive moment in this direction, so we have M, and that is going to be minus 5 kilonewtons times 2 meters. That equals 0. So we get the magnitude of the internal moment, M equals 10 kilonewton meters. Very good. All right, so that's our first free body diagram. Let's look at the second one. Essentially with the second one, because, well, we now know M, we know V, we know N, we can use this as a statics check because they should just be equal and opposite. But what I want to show you is I'm not going to plug these values in. Instead, I'm just going to solve this free body diagram for equilibrium, and you'll see that we're going to end up with essentially the same exact answers. And that will show you that it doesn't matter which side you come from when you're making your free body diagram cuts, that you're going to get the same magnitudes, and as long as you have everything as the same magnitude and opposite directions on different sides of the cut, then you know that you've got everything in equilibrium. So looking at the equations of equilibrium for this free body diagram, we'll start again. We'll start with the x direction. So the sum of the forces in the x equals 0. Well, we have a shear force, V, and we have a negative 5 kilonewtons, and that equals 0. So shear force equals 5 kilonewtons, which matches what we see up above here. Now looking at our forces in the y direction. We get 4 kilonewtons minus 10 plus 6 kilonewtons and minus N. And all of that equals 0. 4 plus 6 is 10, minus 10 is 0, so we get N equals 0. Again, that is consistent with what we've seen up above here. I'm going to come over here and do the sum of the moments. And I'll sum the moments about the cut. And one of the nice things about whenever we break these larger structures into individual elements, it's always good to sum the moments at the cut because you have both the shear force and the axial force have no perpendicular distance, and so you can cancel them out. So you could actually start with this without having to solve the other two. So some of the moments at the cut, we have 4 kilonewtons times 5 meters away, plus, and sorry, that's going in the negative direction, plus 10 kilonewtons times 3 meters away, and then a minus m, and that equals 0. And we'll just put a little line here just to make sure that we don't confuse ourselves. Well, with that m there, and so, yeah, because all of these other forces have no perpendicular distance, so we get a minus 20 kilonewton meters plus 30 kilonewton meters minus m equals 0, and we get m equals 10 kilonewton meters, and we've guessed the direction correctly. So again, same magnitude, and up here I guess we are going counterclockwise, so just make that for consistency. Again, same magnitude, opposite directions. So now that we have all of the requisite forces, we can draw the shear and bending moment diagram. So that's what we're going to do. I'll draw out the free body diagram real quick just so that we have that value, and then we can refer back to what these internal forces are, and we can use a combination of these internal forces and the graphical rules which we learned in the previous video in order to draw out the shear and bending moment diagram. So with that, we will draw the free body diagram again, just so that we have a reference on this page. And it's also useful because then we can see the loading and the shear and the moment all in the same area. So we have 5 kilonewtons here, 6 kilonewtons, 5 kilonewtons, 4 kilonewtons, and 10 kilonewtons, 2 meters, 3 meters, and that's 2 meters. So our shear force diagram. Now keep in mind, were originally asked to draw the axial load diagram, but we found that there is no axial load in any of these members, and so we don't need to draw that diagram there. And we know that because we solved that with equilibrium. So continuing on here, we have our shear force diagram. And I'll just draw the sign convention here. So positive is that the shear force makes the element spin in the clockwise direction. So if it's a beam, it looks like that, but again, same sort of clockwise bit. If it's a vertical element, it'll be in this direction, and the units are kilonewtons. So our shear force diagram, if we have we'll draw it here, and we'll put some quick dimensions on here for this. Do 2 meters, 3 meters. Let me fix that meter sign up there, and 2 meters. So our shear, and we'll draw our shear force diagram in red just so that it stands out. Remember, if we're using our graph, so we have two options. We can either take more free body diagrams and generate an equation, or we can use the graphical rules we've learned on how to draw shear body diagrams, shear force diagrams. So we'll use the graphical rules. So we know that we have a force going up of 4 kilonewtons. Then we have no change in shear force because we've got no change in loading. So until we come to our applied load, we maintain a 4 kilonewton shear force. Then our 10 kilonewton, we're going to push it down 10 kilonewtons, and then we have no change in loading. And so it comes around until we go up 6 kilonewtons. and our shear force diagram closes, which is a good check. We are in equilibrium, and I will put just the direction of the shear on the diagram just to be explicit. And then up here at the top, we are going over 5 kilonewtons until we come down and come back in 5 kilonewtons. So that all makes sense, and it's a pretty straightforward shear force diagram to draw. Now we'll draw our moment diagram. And put our sign convention. So for if we are a horizontal element, positive bending is going to be when the compression is, when the top is in compression, and then I'll draw another element. We'll just rotate that 90 degrees, and we'll say it's positive if the left-hand side is in compression. Now which direction is positive and negative is more a sign convention aspect, but what will be an important bit of how we draw shear and moment diagrams is that we are going to plot them on the tension side. So if the portion of the element is in tension, well, that's where we will plot the element. And again, if you ever get confused, remember the tension side is where the tail of the arrow is. So drawing our little frame again. Now, what are we going to do? Well, we're going to use what we found previously, and we'll start with this vertical element. So we know that at the end, there is zero moment because it's a free end. It can't generate any moment. Similar to where we have this roller support and a free end, we can't resist any moment there. So we know that both of these points are zero. Then if we go back to our free body diagram, we know at the base of the vertical portion, the moment equals 10 kilonewton meters. And if we have using our graphical rules, we know if we have a constant shear force, we know we will have a linear distribution of moment. And with that linear distribution of moment, we also know that, and then now which side do we plot it on? Well, the element is pushing this direction. That means that it's going to bend over. It means that this backside is going to be in tension. So let's just go ahead and draw that in tension, and we know that value is 10 kilonewton meters, and we'll put the direction it's getting bent on. So, yep, that makes sense, and that makes physical sense in terms of, we know that force is pointing to the right, and it's going to bend that cantilever over. Now, for the beam section, we can use our graphical rules from the shear force diagram, and we know that if we have, again, a constant shear, we're going to have a linear distribution of moment. So, and we know that, we're pushing down, so we're going to bend the beam in a banana, and the tension side will be on the bottom. And we will go until we then change directions, and then we have a negative shear, and so we will change our slope. And if you remember, our slope is going to be opposite of what the shear force is. And also, again, at this right at the end, we have an equal and opposite moment of 10 kilonewton meters the other direction. So we know here at the corner, we also have 10 kilonewton meters. It's going to be a happy beam there. It's going to be a sad beam there. And in the corner, they overlap, and they're going to be equal and opposite. So now the only thing we need to know is what is the value of the moment here. If you recall from the previous video, we can find the moment by just taking the area of the shear force diagram up into that. So we would have 4 kilonewtons times 2 meters, and we end up with 8 kilonewton meters. And if we were to take a free body diagram cut right at that same location, and we were to find the internal moment, that's exactly what we would end up getting. And that's really all we're doing when we do this graphical method with the shear force diagram. So a final little note before I sign off here, and this is really around the shear force diagram on the corner. It's important, so I'll write it out explicitly. And that's that moments at corners are equal and opposite. And so the way that will manifest itself on a bending moment diagram is if you have a corner and if you only have two elements coming in, I'll draw out two different corners just for sort of two different scenarios that you would see with these bending moment diagrams. So you will either have both on the outside. So I'm just going to draw a uniform. And again, the outside, they're going to be bending this way. Where we're plotting on the tension side here. Or they will both be on the inside. And if they're on the inside, again, the tension side, we're going to be going like this. And the important part is that these two moments will be the same magnitude. So this is really showing that we're going to be equal and opposite. That's what it looks like graphically. So it's always a good check when you have these corners and you do draw your bending moment diagrams. Do you end up with values and plots that look like this? So with that, we'll just wrap up with this brief introduction and short example on how to do bending moment diagrams when you have a corner. So thank you very much.